In this video, I'm going to go through the Edexcel AS paper, paper 2, Organic and Physical Chemistry, and this is the 2018 paper. Okay, and I'll just do the first half of the paper in this video and the second half in the next one. Okay. So, which of the following does not act as a nucleophile? Well, the answer is HBr. That's actually usually considered to be an electrophile. The delta positive hydrogen will be attracted to areas of high electron density. All the others will react with, for example, haloalkanes. So you'd have a delta positive on the carbon, which is attached to the bromine, and they've all got, so NH3 has got a lone pair on an electronegative nitrogen. Water has got a lone pair on electronegative oxygen, and the cyanide, where you've got a negative charge, a lone pair on the carbon. And they will all be attracted to the delta positive carbon in the haloalkane. Right, this question about the molar volume of gases. Calculate the volume of 1 mole of an ideal gas at that temperature and that pressure. Okay, so we need the ideal gas equation. So what to give it us, PV nRT. Rearrange, so we get V is equal to nRT over P. And I think we've got to be really careful with the ideal gas equation are the units. Okay, right. So the units, strangely, are in meters cubed. Okay, and so our volume, meters cubed, is going to be equal to the number of moles, which is 1. The ideal gas constant, 8.31. The temperature has got to be in kelvins, so that is 273 plus 60, that's equal to 333 Kelvin. And the pressure can't be in kilopascals, it must be in pascals, so that's 500 times 10 to the power of 3. And that works out to be, right, 5.53 times 10 to the minus 3 meters cubed. Fine to leave it in meters cubed, it doesn't say you've got to convert it or anything, but as long as you do state the units. And two significant figures, so I should just give that to 5.5 times 10 to the minus 3 meters cubed. It does say in the question there two significant figures, yeah. Right, here we've got to calculate the MR of a gas from its density. Okay, so we've got this gas B, and it's got a density of 1.42 grams per decimeter cubed. Right, now it tells us the molar volume of a gas. So 1 mole occupies 24,000 centimeters cubed. Seeing as they give us our density per dm cubed, let's convert this into dm cubed. So that's going to be 24 dm cubed. That's how much 1 mole occupies. Okay, so what we're going to say is density is equal to the mass over volume. So we want to find out the mass of 1 mole. So the density is equal to the mass of 1 mole divided by the volume of 1 mole. Okay, let's put the numbers in there then. So the density they tell us is 1.42, so we get 1.42. Now the mass of 1 mole is, of course, the MR. That's equal to the MR, the relative molecular mass. So let's write that down there. MR over the volume of 1 mole is 24 dm cubed. So MR is equal to 1.42 multiplied by 24. That is equal to 34.08. Right, now it tells us the gas is XH3. So we've got to find out the identity of the element X. Well, first thing that's spring to mind, I suppose you can think you've got ammonia, NH3, but that doesn't, that's not the MR of that, it's only 17. So anyway, let's just say take away 3 from that. X must have, has an atomic mass of 34 minus 3. That's for the 3 hydrogens, which is equal to 31. And if you look in your periodic table, that is phosphorus, that element. and it probably would form, well, it does form a hydride with the formula pH3. It's in the same group as nitrogen. It's in group 5, so that all seems to be right. Okay. Right. B, we've got an experiment here. So you've got some sodium carbonate reacted with hydrochloric acid. I'm going to collect the gas produced. So this is what they do. All right. Solid sodium carbonate is placed in the container, weighed accurately. Okay. The delivery tube rubber bung removed and the sodium carbonate transferred into there. Then we're going to reweigh the container to find out the mass of sodium carbonate. Sodium carbonate solid in there. Push the plunger down to 0, step 4. Step 5, they're going to add some hydrochloric acid, okay? And we can work out the number of moles of hydrochloric acid there because they give us the volume and they give us the concentration. Right, we're going to get a reaction. So reaction there where gas is going to be given off, carbon dioxide gas. The mixture is shaken. So when you add the acid, they put the rubber bung in there and seal it. So obviously we're going to get a bit of gas escaping there probably before you manage to get the rubber bung in. To remember that for later. Okay. And here is the equation for the reaction. So we've got sodium carbonate plus hydrochloric acid, and it gives us makes carbon dioxide gas. Okay. So they've done the subtraction for us here. The mass of the sodium carbonate added is, is that number minus that number, 0.242 grams. Okay. First of all, let's calculate the moles of hydrochloric acid and the moles of sodium carbonate. Right. Let's do the hydrochloric acid first. So moles HCl is equal to the concentration times by the volume. The concentration is 0.4. And the volume is 10 centimeters cubed, so 10 over 1,000 dm cubed. That gives us 4 times 10 to the minus 4 moles, 4 times 10 to the minus 3 moles, sorry, of HCl. Now let's do the moles of sodium carbonate. Well, that is equal to mass over mR. We know the mass of sodium carbonate we've added. So the mass we've added is 2.42 grams. And the mR of sodium carbonate is 106. They tell us that. And that gives us the number of moles there as 2.83 times 10 to the minus 3. Okay, now we've got more moles of HCl, but we have to be, than sodium carbonate. We have to be careful here because we need to look at the molar ratio. And here's the equation. Look, 1 mole of sodium carbonate requires 2 moles of hydrochloric acid. So look, we're going to need twice that amount of HCl to react with all of that sodium carbonate, and that's going to be obviously going to be more than 4. So we can say here that the sodium carbonate is in excess. Double that, I think you would need, what was it there, you'd need whatever that is, 2 times 2. You need 4.56 times 10 to the minus 3, and we haven't got that much. 4.56 times 10 to the minus 3 moles of acid. So the sodium carbonate is in excess. Okay, right, the actual volume of the carbon dioxide, no, right, use your answer to calculate and then calculate the maximum volume of carbon dioxide. We've got to do this bit here, which could be produced. Well, the amount of carbon dioxide is going to be controlled by the amount of hydrochloric acid because that is the reactant that is limiting, okay? So 2 moles of HCl, it will give 1 mole of CO2. We don't have 2 moles, we have 4.5 times 10 to the minus 3. So 4.0 times 10 to the minus 3 moles. That will give 4 times 10 to the minus 3 divided by 2, which is equal to 2.0 times 10 to the minus 3 moles CO2. Right, so we know the number of moles, so now we can work out the volume, because we know the volume of 1 mole is 24,000 centimeters cubed. So what's the volume of 2 times 10 to the minus 3? So we'll do that. So volume of carbon dioxide is equal to the number of moles multiplied by the volume of 1 mole, 24,000 in centimeters cubed. So 2 times 10 to the minus 3 times 24,000 gives us 48 centimeters cubed. That's the volume of gas we would, the maximum volume we could get. Right, now he says the actual volume of carbon dioxide was less than calculated. Give 2 reasons for that. Right, the most obvious reason, the one I mentioned earlier, is because you put the acid in, then you have to quickly put the bung in before any gas escapes. So gas will escape before the bung is placed. In the tube. And also its carbon dioxide is reasonably soluble in water. Okay. And you've got aqueous hydrochloric acid, so in the tube there, so a little bit of CO2 will dissolve in the hydrochloric acid in the tube until it's formed a saturated solution. Then the rest of will be gas. Okay, now I've got a question about the oxidation of ammonia, and it's an equilibrium reaction here. Write the expression, the Kc expression for this. Right, so Kc, concentration of products, so that's going to be the concentration of N2, square brackets, the concentration of, to the power of 2, because we've got that coefficient there, multiplied by the concentration of H2O, gas, to the power of 6, divided by the concentration of ammonia, to the power of 2, sorry, by power of 4, and the concentration of oxygen to the power of 3. Now the units there could be quite complicated. Well, if you look at the top, we've got a 2 and an 8. So that means we've got mole per decimeter cubed. We've got concentration terms to the power of 8. 2 plus 6 make 8, sorry. And on the bottom, we have got concentration terms, right, 4 and 3, add them together, it's 7. So we're going to have mole dm to the minus 3 to the power of 7. Right, that is going to simplify, of course, to moles per decimeter cubed. Just like if you had like x to the power of 8 divided by x to the power of 7, that's just equal to x to the power of 1. Okay, so that's the units there. Right, nitric acid is made from ammonia. One of the stages in nitric acid production involves the oxidation of ammonia to produce nitrogen oxide. In this process, a mixture of ammonia and oxygen is passed over a catalyst. Okay, and they give you the temperature and the pressure there. Use the equation and the enthalpy changes the formation of nitrogen to oxide and water to calculate the enthalpy change for formation. So we're trying to find out delta HF of ammonia here. Right, now they tell us that, I've written the equation out again here, and we know that the value for that, delta H for that, is minus 904.8. Now when you're given delta HF values in Hess's law cycle, the third thing that you should have down, you should have 3 things in your cycle, is you should have elements in their standard states here. So the elements in the standard states are going to be N2, we're going to have 2 of those. We've got hydrogen, we've got 6 hydrogen atoms, sorry, 12 hydrogen atoms, so that's 6H2, and we've got 10 oxygen atoms, so that's 5O2. So there's the elements in the standard states there. Now, do we draw the arrows up or down? Well, when we form things, we form them from the elements in the standard state. So when that arrow is going to go that way, because we're forming 4 moles of NO and 6 moles of H2O there. On this left-hand side, we are forming 4 moles of ammonia, so the arrow goes up there. Right, so now let's put the numbers in. So, right, here we're making 4 moles of, I'll just scroll down a little bit. Oh, I've got it here. 4 moles of NO. Okay, and delta HF for that is plus 90. So we're going to have 4 times 90.4, and that's all positive. And we're also forming 6 moles of gaseous water, so that's going to be 6 times minus, that's a negative value. Right, let's put all that into a calculator. So 4 times plus 90.4, add 6 times minus 2412, you get a value there of minus 1088, sorry, minus 109.2 there. Here, well, what we're doing, 5 moles of oxygen, that's an element in steady state, that's 0, so ignore that. But here, well, we're forming 4 moles of NH3, so let's call that delta HF for ammonia. Let's say that's equal to X, so we're going to have 4X on that red arrow there. Right, so now we have to do a bit of, I'll put all those in, so we can see this blue value here, minus, I drew a little, so we've got minus 9408, 904.8 is equal to, right, what we're doing with this red, right, so we're going to go there, and then we're going to go there. So we're going against the red arrow, so we change the sign, so that becomes minus 4x. We're sticking with the direction of the green arrow, so that stays as a negative, so that's minus 109.2. Right, let's just do a bit of algebra on that then, and we get minus 4x is equal to minus 904.8 plus, that becomes a plus because it goes on the other side. Simplify that, minus 4x is equal to plus 184.4. So x, divide that by 4, gives us minus x, sorry, gives us 46.1. So x is equal to minus 46.1. And x, of course, is delta HF for ammonia. So the answer is 46.1 kilojoules minus, sorry, 46.1 kilojoules per mole. Right, calculate the atom economy by mass for the formation of NO in this reaction. So, all right, atom economy is equal to the mass of useful products over the mass of all the products multiplied by 100. So the useful products are 4 moles of NO. Well, what's the mass of that? Mass is equal to moles times MR is equal to 4 times, well, it's 30 for that, which is equal to 120. 120 grams of that. And then we've also got 6 moles of water. Write this down here, 6 moles of H2O. Mass times MR, that's going to be the mass of that is going to be equal to number of moles 6 times by the MR of water 18, which gives us 108. So let's put the numbers into our atom economy. So we get 120 over 120 plus 108 times 100, and that works out to be 52.6%. Okay. Number of significant figures, I would give it to 3 SF, because all ARs, they're usually given to 3 SF. Okay. So I'd leave it as 52.6. Right. Need to rub this out, so we're going to answer this question. Right. What would happen if you increased the pressure? What would happen to the rate? They're trying to confuse you with equilibrium here, but right. If you increase the pressure, the rate will increase for any gaseous reaction. Why? Because the particles are closer together, gas particles closer together, so they're more likely to collide. Increase the pressure of a gas, it's almost like effectively increasing the concentration of the gas, okay? It's going to increase the rate of reaction. Right, the catalyst used is a heterogeneous catalyst. State what is meant by this term and why it has no effect on the yield, okay? Right, heterogeneous catalyst means that the catalyst and the reactants and products are in different phases. And what that usually means is the catalyst is a solid and the reactants and products are gaseous. That is usually the case. Okay, why doesn't it affect the yield? Well, adding a catalyst never affects the position of equilibrium, because the catalyst will increase the rate of reaction at the rate of the forward and backward reaction equally. Okay. Diagram shows a Maxwell-Boltzmann distribution of particle energies, okay, including the activation energy. Right, and an increase in temperature will increase the area under the curve. That's wrong. The area under the curve is proportional to the total number of gas molecules, or particles, I should say. And that stays the same, so that doesn't change, so that's wrong. We'll move the peak of the curve to the right. Yeah, it will move it to the right, because that means it's going to move it like that. And I've drawn that peak lower, so it's got the same total area under the curve. But you can see that the sorts of most probable energy has gone from here. It's increased to there. Well, that's what would happen if you increase the temperature. So that one's right. Let's just check the others. Will it raise the height of the peak? No, you can see that the peak has got to be lower, because the area under both curves has got to be the same, because the total number of particles has got to be the same, and the area under the curve is equal to the number of particles. And of course, changing the temperature doesn't change the activation energy. Add a catalyst, that will change it, but not the temperature does not affect it. So B is the right answer there. Okay, some organic chemistry now. Okay, halogenoalkanes. So we've got 1 chloropropane. Now let's just see, before we read the questions, let's see what's happening. Right here, reaction 1, this is elimination. We've removed an HCl to form the alkene. Here we've replaced, in the reaction 2, we've replaced the chlorine with a cyanide group, so that's nucleophilic substitution. And in here, reaction 3, this is also a nucleophilic substitution, because we replaced the chlorine with an NH2 group. Right, the reagent conditions used in reaction 1 for elimination. Right, it's got to be NaOH, or usually they say KOH, but NaOH is fine. But the important thing, it's got to be in ethanolic solution, not in aqueous solution. It must be in ethanolic solution. In aqueous solution, you'd get nucleophilic substitution and you'd form an alcohol. So that's what you want there. Right. Probably 1 mark for each there. 1 mark for the reagent, 1 mark for the ethanolic solution. Identify a suitable reagent for reaction 2. Right, we've got to swap for cyanide. So we would want the cyanide ion, Cn minus, okay, so that's usually provided as potassium cyanide, okay. Why is this a particularly useful type of reaction? Because you create a new carbon-carbon bond, or you could say you've lengthened the carbon chain by 1. It's essentially saying the same thing. Why in reaction 3 is it heated in a sealed container? Well, why is it heated? That's to increase the rate of reaction because it's too slow otherwise. Why is it going to be sealed? Well, it's because NH3 is a gas. And if you heat it's an aqueous solution, a concentrated aqueous solution, but if you heat it, the gas will be lost from the reaction vessel. And of course, you couldn't use a reflux condenser because it's a gas, it's not a volatile liquid, it will just go. It's got to be sealed. Okay. Right. Question 4. Write the structural formula of the product that will be formed if 1-chloropropane is refluxed with aqueous potassium hydroxide. Well, we are going to get nucleophilic substitution here. So I will just, I'll write down. So 1-chloropropane is obviously like that. But as for the product, well, we're going to swap that that chlorine for an OH minus, so we're going to get propan 1-ol. Should put those H's in there. Okay, so that is the form. That's what you'll get there. Right, now this question is about the relative rates, okay, of hydrolysis. I'll make this a tiny bit bigger, I think. Okay, bromoalkenes X, Y, and Z were added to a mixture of aqueous silver nitrate and ethanol at 50 degrees C. The rate of hydrolysis was compared, okay, by the time for a precipitate to appear. So what's going to happen here is the water is going to act as a nucleophile. That's going to go there, and you're going to lose the halogen as a halide ion. And the halide is going to come off. Br minus is going to react with the Ag plus in the silver nitrate solution to form AgBr. Right, which one is going to react the fastest then? Well, we need to look at what kind of haloalkanes these are. So this one is a secondary haloalkane because you see the bromine is attached to a carbon which is attached to 2 other carbons. This one is a primary haloalkane. And this one is a tertiary haloalkane. And you should remember that the tertiaries are the fastest. So that's going to be the fastest. So Z is going to be the fastest. And Y, the primary, that's going to be the slowest. So it's Z, X, Y is the order. That's the right one. And if you remember why that is the case, is because tertiaries can react via a slightly different mechanism, via a carbocation, and that is faster than the way primaries react, which don't go through a carbocation, and the secondaries, you get a kind of mixture of the two going on. So that is the order there. Right, question concerns alkenes and some halogen compounds. The alkene propene reacts with hydrogen chloride. This is best described as, right, how does propene react with hydrogen chloride? Here's propene. Hydrogen chloride is an electrophile, okay? So that's hydrogen bromide I've just drawn. Same mechanism. So hydrogen chloride, you're going to have a partial positive charge on the hydrogen because of the electronegative chloride ion. and the start of the reaction is the pi electrons jump onto that there. Okay, now so it's electrophilic. This is an electrophile, and it is not substitution, it's addition. Okay, it's this one, because you end up breaking the double bond. Okay, so that is an addition reaction. The reaction of propene with hydrogen chloride can produce two isomeric products. Okay, one chloropropane and two chloropropane. What are they? Are they EZ isomers or stereoisomers? No, they're not. They are just straightforward structural isomers. They have a different structural formula. Okay, draw the mechanism for the reaction of propene with hydrogen chloride to produce 2-chloropropane. Include curly arrows and irrelevant dipoles. Okay, so I've actually started that up here. So I think I'll finish that off up here. Right. Right, so what happens is that I've drawn the dipoles, the important dipoles, which is the partial charge on the hydrogen. Okay. And when the pi bond breaks there and this curly arrow goes on to the hydrogen, then the pair of electrons between the hydrogen and chlorine has got to break. Right, now the hydrogen can stick to either that yellow carbon or to that purple carbon, but to produce 2-chloropropane is going to stick to the purple one. So let's draw that. So we end up with this intermediate. There we've got our new hydrogen stuck onto that carbon there. Right, now the middle carbon is only forming 3 bonds, and it is actually a carbocation. You have a positive charge on that. And the chlorine has come off as a Cl- because it gets both of the electrons in this bond here. So this is Cl-. And the final step in the mechanism is for the lone pair, one of the lone pairs on the chloride ion, to go onto that carbon there to form a new bond. And the product we have got is the chlorine there, 2-chloropropane. So that is our mechanism there. It's pretty straightforward recall. Okay, we've done that question there. B, okay, halogenoalkane chloroethene is used to make the important polymer PVC. Draw a displayed formula of 2 repeats of polychloroethene. So let's draw chloroethene. So chloroethene, we have got a chlorine on one of the carbons. And well, let's draw what's going to happen here when they polymerize. So I've drawn 2 monomers there, and so this is going to give us 2 repeat units. So what happens is we break the double bond there, and we form a new single bond between those 2 carbons, and of course the single bond is going to the next one along, and that single bond is going to the next one along there. So there's 2 repeat units of it, and that's displayed. I've drawn every bond there. Okay, question 2. Some polymers are disposed by incineration. Right, why isn't incineration suitable for disposal of PVC? Well, it's because it hasn't just got carbons and hydrogens in it, which is going to give you CO2 and H2O. It's got chlorine in it, and when you just incinerate that, you will get HCl gas, which is acidic and corrosive, and you can't release it into the environment. Right, chloroethene has a boiling temperature 260 K and is known to be carcinogenic, so that means it's known to potentially cause cancers. Right, now boiling temperature minus 260 K, right, room temperature, sorry, 0 is 273 Kelvin, so that means this is a gas. Right, it's a gas that can cause cancer, so it should be only used in a fume cupboard. I think that's the point they're trying to get across there. Okay, right, chloroethene can be manufactured by a 2-stage process. Chlorine is reacted with ethene, okay, at this between 50 and 80, okay. One reason why temperature below 50 would not be used, right, below 50, the rate of reaction would be too slow. At low temperature, the rate would be too slow. Now, why not above 80? Well, why not above 80? Well, if we look at this, this is an exothermic reaction. So Le Chatelier's principle tells us if you increase the temperature too much, the equilibrium will move to in the endo direction, will move to the left. So the equilibrium yield of the product will be too low if the temperature's too high. So one reason about rate and one reason about equilibrium. In stage 2, the product of the first reaction is converted to chloroethene. Okay. Both products are required for use, so they're both useful, the chloroethene and the HCl gas. Which method would be most suitable for the separation of these two products? Right. Right, fractional distillation, I don't think it would be that one. It would work, but it's going to be tricky because they're both gases. So, you know, you wouldn't be able to do it at room temperature. You'd have to be at a lower temperature. Heating under reflux is just a red herring, of course. That won't separate anything. Bubble through dilute alkali. Now, that would remove the HCl because the HCl is acidic, but that's no good because it would convert it into, it would destroy the HCl, it would convert it into a salt. So that's no good. You need both products. So it's got to be this one, solvent extraction using a separating funnel. And I think if you use water, for example, HCl is very soluble in water, and this stuff, because it tends to form, it's a non-polar molecule, it would be insoluble in water. Okay, so the HCl would dissolve in water, so you'd have your separating funnel. Water's probably very lighter than, because it's got a chlorine atom in it. Okay, this is nasty, this, but anyway, you've got H2O there, and the HCl would dissolve in that. And here you would have your you just have your chloroethene. It wouldn't dissolve in the water very well. Okay, so that would be the best, and we'll tap on this separating funnel. That would be the best way of doing that. Right, that's about halfway through the paper, and so I'll do the next half in the next video.